In this lecture, we are going to explore polymorphism in Python. Polymorphism is a key concept in object-oriented programming, and Python handles it in an intuitive way. First, we'll introduce what polymorphism is and why it's important. Then we'll explore its various forms, such as compile time and runtime polymorphism, and how Python emulates method overloading. We'll also look at how polymorphism works with functions and classes, and how it plays a role in inheritance. Additionally, we'll cover abstract base classes and how they relate to polymorphism. Finally, we'll wrap up with a discussion on duck typing. Let's begin. Polymorphism comes from two Greek words, poly meaning many and morph meaning forms. So polymorphism refers to something that can take many forms. In Python, it refers to the ability of different objects to respond to the same method call in their own unique ways. This helps make our code more flexible and extendable. It's one of the four pillars of object-oriented programming, alongside inheritance, encapsulation, and abstraction. By using polymorphism, we can write cleaner and more adaptable code, since objects of different classes can be treated as instances of the same class through a shared interface. There are two types of polymorphism we need to talk about: compile-time polymorphism, which includes method overloading, and runtime polymorphism, which involves method overriding. Method overloading refers to defining multiple methods with the same name but different parameters. Python doesn't support this directly, but we can use default or variable length arguments to achieve a similar effect. Method overriding occurs when a child class provides a specific implementation of a method that is already defined in its parent class. First, let's talk about method overloading. In other languages like Java or C++, we can have multiple functions with the same name but different parameter lists. This is called method overloading and happens at compile time. In Python, though, we don't have method overloading in the traditional sense. However, we can emulate it using default arguments or variable length arguments. Default arguments allow you to assign default values to parameters in a function. This means if you call the function without providing those arguments, the function will use the default values. Let's look at an example. I'll create a new folder for our polymorphism practices and then add a new file called polyemulate.py. We'll define a function called add, which takes three parameters. The first parameter, a, is required, while b and c have default values of 0. This means we can call the function with 1, 2, or 3 arguments. If we only provide one argument, the function will use the default values for b and c. The function then returns the sum of all three parameters. This approach allows us to handle different numbers of arguments with a single function, offering flexibility without needing to overload the function. When we run this script, we see that all the three forms work. This simulates overloading by using default arguments. We could also use variable length arguments, or args, to mimic polymorphism. As we already learned, this feature allows a function to accept a varying number of arguments. Let's modify our function using args. Inside the function, args is treated as a tuple containing all the arguments passed. Now we can use our function for adding any number of arguments. If we run the code again, we should see any of the forms work. By using args, the add function can handle any number of arguments, mimicking polymorphism without the need for explicitly defined parameters with default values. As a result, even though Python doesn't support compile-time polymorphism directly, we can mimic it by using features like default or variable length arguments. Now moving on to method overriding, which happens at runtime. This is when a method in a subclass has the same name as a method in its parent class, but the implementation in the subclass is different. To better understand method overriding, let's create a new example called polyruntime.py. In this example, we'll define two classes, a parent class, which we'll call animal, and has a method, sound, and a child class, dog, that will inherit from animal and overrides the sound method to return bark instead of the generic sound. Now, let's instantiate both and call their sound methods. When we run this code, we'll see that even though both classes have the same method name, the output depends on the object calling the method. This is polymorphism in action, with different behaviors for the same method name depending on the object type. Let's extend our example by adding two more subclasses. A subclass cat, which overrides the sound method and returns meow, which is specific to cats. And a subclass pig, which does not override the sound method and stays with the generic sound from the animal class. Then we'll create instances of the cat and pig classes and call their sound methods. At this point, if we run the code, we'll observe that the cat object uses its own sound method, whereas the pig object will use the default sound method inherited from the animal class, as it didn't override the method in its own class. This is a great example of runtime polymorphism, where the behavior of the sound method is determined at runtime based on the type of the object. Sometimes we want to enforce that certain methods are always implemented in child classes. This is where abstract base classes, or ABCs, come into play. ABCs allow us to define methods that must be overridden by any subclass, making our design more structured. By using abstract methods, we ensure that every subclass provides its own implementation of critical functionality, giving us a stricter form of polymorphism. We need Python's ABC module to create abstract classes. These classes can't be instantiated directly. Instead, they serve as blueprints that force subclasses to implement specific methods. Let's convert our animal class to an abstract class. Firstly, we need to import the ABC and abstract method from Python's ABC module. Then, we'll change the animal class to an abstract class by inheriting from ABC and marking the sound method with abstract method. This tells Python that the sound method must be implemented in any subclass. The method doesn't do anything here because it's just a placeholder. At this point, the dog and cat classes are already good, since they have overridden the sound method with their own implementations. However, if we try to create a pig class without overriding sound, Python will throw an error. So, let's go ahead and override the sound method for the pig class to make it return oink. This will ensure that the pig class follows the rules set by our abstract base class animal and provides its own implementation for the sound method, just like dog and cat do. Additionally, we can't instantiate the animal class directly. Python prevents this because abstract classes are meant to serve as blueprints for other classes and aren't intended to create objects on their own. So let's make sure to remove any instance of animal or calls to its sound method. Instead, we'll work directly with the subclasses, which provide the specific behaviors we want, like dog, cat, and pig. Let's now run the code and observe how the objects from the different inherited classes behave. As expected, each object, whether it's a pig, dog, or cat, calls its own sound method. This shows how polymorphism works. Though all classes inherit from animal, each provides its own sound method. Finally, we come to a key concept in Python's dynamic nature: duck typing. Python doesn't require objects to be part of a formal inheritance structure to exhibit polymorphism. With duck typing, we simply focus on whether an object has the correct behavior, regardless of its actual type. The famous phrase is, "If it looks like a duck and quacks like a duck, it must be a duck." This flexibility is a unique strength of Python, allowing us to treat different objects in the same way based purely on their behavior. Let's create a new example called polyduck.py and see how duck typing makes Python's polymorphism even more powerful. In this example, we have a car class and a bike class, both with a method, move. Even though these classes aren't related through inheritance, Python's polymorphism allows us to treat them similarly as long as they have the same method. Now, we'll define a startMoving function that takes a vehicle parameter and calls the move method on it. Here's where duck typing comes into play. Python doesn't care if the vehicle is a car, a bike, or anything else. As long as the object passed to the function has a move method, Python will happily call it. Let's create instances of car and bike and pass them to the startMoving function. Each object will execute its own version of the move method. If we run the script, for the car, it will print car is moving, and for the bike, it will print bike is moving. Even though these classes aren't related, we can handle them similarly because they share a common method. This is the power of duck typing in Python, demonstrating polymorphism without inheritance. Let's quickly recap what we've covered. We started by defining polymorphism and discussed why it's important in Python. We looked at two types of polymorphism: compile time, emulated through flexible arguments, and runtime, via method overriding. We saw how to emulate method overloading using default and variable length arguments. We explored polymorphism in functions and classes, including how overriding works with inheritance. We introduced abstract base classes to enforce method implementation in subclasses. Finally, we talked about duck typing, which lets us handle objects with similar methods, even if they're not related by inheritance.